So today we want to continue looking at contours and level curves. And the strategy is just a modification of an old strategy that we've used before. We're going to assign constants to one of the variables a bunch of times. Assign constants to one of the variables a bunch of times. We're just going to assign constants to one of the variables a bunch of times. Balance it out. No, it only has panic mode. It's too bright in the background. And I turn the lights down. It's like, it's too dark in the background. I think this is a little bit better. This is a thing that we did before, right? If I had a function of one variable, that's how we produce the graph. So this is just like when we produce the graph of a function of one variable. This is just like graphing y equals f of x. Back in the day, when we didn't know what stuff looked like. We'd make a table of values. We'd assign a bunch of constants. We'd get the outputs. And then we'd use that to produce a graph. Just plugging in a bunch of constants and plotting the height above the x-axis. We do a similar thing when we're looking at level curves. We pick one of the variables let's say we have an equation with three variables. Not that maybe we can write z as a function of x and y, or x as a function of y and z. Maybe we can't. We got an equation in three variables, and we look at level curves. We pick one of the variables. We plug in a bunch of constants. Just like before, we plug in a bunch of constants, but instead of the output just being a number, instead of the output being just a number, our output is going to be an equation with two variables, which will produce a curve in R2. So it's a little bit harder to summarize in a table because when z is equal to 0, we get 0, 0, just that 1 point. But when z is equal to 1, we had a circle of radius 1 centered at the origin. When z is equal to 2, down here in this row, we would write circle of radius square root of 2 centered at the origin. When z is equal to 3, and so on. We'd have a circle and so on. We're just plugging in a bunch of constants to see what we get. We could do this the other way. We could flip these around and plug in x's and y's and find the heights and produce a surface that way. But we're trying to look at it in a different way. Any questions? We could have done the same thing back here. We could have figured out, taken values of y, say, well, what will produce this output? And then solve the equation to get back to the x and say, now I have another point. I can put that on my graph. But it's the same thing. We just plug in a bunch of values to see what's going on. There's really not a lot of techniques that we have when we're starting out. It's kind of like at the bottom of every scientific endeavor. Guess and check. That's it. That's all we ever do. We make a guess and then we check. The important part is keeping track of all the guesses that we've had before so that we don't have to make those again. So back when we were trying to look at graphs, before we didn't know what stuff looked like just based on its equation description. So we encountered y equals mx plus b. But then we graphed a bunch of them, and now we have knowledge. Then we got to learn y equals mx plus b is going to look like a line, a slope of m and a y-intercept of b. When we see an x squared graph, we know we're going to get a parabola. Y equals x squared is going to produce a parabola. And variations, if it's just an x squared and an x squared is the biggest one, we know we're going to get a parabola. It's going to open up or open down. So we build a library in our minds of graphs. So this process has produced a library of graphs. Y equals mx plus b, that's a line. We recognize what that's going to look like. Just seeing the equation. Seeing the equation triggers that picture in our mind. When I say y equals mx plus b, most of you imagined a line with a positive slope. Mind reading 101. Play the percentages. Pick a number between 1 and 10. 3. Someone's going to pick 3. In a group this size, definitely someone's picking 3. If you think they're trying to get over on you, pick 7. Just play the percentages. But all we're trying to do is build a library of things that we can see based on the equation. I didn't draw a line. I just wrote y equals mx plus b. But in our minds, we've made that connection. It's a line. Oh, I should say y equals ax squared plus bx plus c. If I see y equals ax squared plus bx plus c, I know we're going to get a parabola. Moreover, because of the position of the y and the x, I know it's going to open up if a is positive and open down if a is negative. That's based on our experience. It wasn't just because someone said y equals x squared is going to produce a parabola. Someone probably did just say that to you, but then they followed it up with graph all these functions to put that connection together so that you would recognize that. Then from there, you can start learning variations. So if I say x is a times y squared plus by plus c, it's also a parabola, but it's going to be horizontal, and they're harder to draw horizontal. Because we've combined that core piece. Y equals x squared is a parabola. Expand that to ax squared plus bx plus c. That's also a parabola. If we switch the roles of the x's and y's, we know we just turn things 90 degrees. So if y is a function of x, just take your function of y and flip it 90 degrees. Any questions? This is why math is so simple. We're just taking old ideas and piling more on top of it to try to exploit the things that you already know and to expand your entire knowledge base. This is why math is so difficult, because all the new stuff we're handing you is going to be built on that foundation of the old stuff. And so if that is a little bit shaky, if you're not really clear on this parabola business, then if I start writing them sideways, it really starts messing with you because you weren't really solid on this one. And then I started doing more stuff to that. Does that make sense? This does not mean that we have to wait until this is perfectly solid before we move on. We are not literally building a house. It's fine to just move on with a shaky foundation, so long as you warn people that that's what you're going to do. So in light of that, quick warning, it's okay if you don't remember all of your derivatives and integral stuff. It's okay if you're shaky on that. We can still move on, because sometimes moving on will end up shoring up the stuff that we had before. We'll find holes in your knowledge to this point, and then we'll be able to fill them in. That makes sense? This is, in my experience, how things work. Don't worry if you have a couple of deficiencies in algebra, because you do. We can fill them in as we go. Here's another example. Does everybody remember partial fraction decomposition? Heck yeah, it was awesome, right? It's how to break apart fractions in a particular way. It's like we know how to add fractions. Do we know how to unadd fractions? It's not even subtraction. It's not the inverse. It's unadding them in a particular way. That's purely algebra. You don't encounter it until Calc 2, but it's purely algebra. You technically, after you teach people how to add fractions, I go, well, you know how to add fractions. You know how to factor polynomials. Let's unadd some fractions with some partial fraction decomposition. We don't do that anymore because it leads to open revolt in your algebra classrooms. And we've lost a lot of good math teachers in those kind of revolutions. So we sat down at the table, said, all right, we will take partial fraction decomposition out of the algebra and move it later on. And then the students all high-fived each other and said, oh, I told you we didn't need that. And all the teachers said, they still don't understand what we're doing. It's okay, I'm not making fun of you for not understanding what we're doing here, because a lot of teachers don't understand what we're doing here either. But that's okay. Like I said, you can move forward in math on a shaky foundation, because it's not literally a house. Any questions? So yesterday, we started to build on that circle idea, and we started to use that circle to find some surfaces, to start building our library of surfaces. So we are now building a library of surfaces. One that we saw yesterday, z equals x squared plus y squared, is a circular paraboloid. We envisioned it in sections. From the top, for fixed values of z, we saw a bunch of circles. They got closer together as z went up. And that made sense because when we looked at it from the side, we saw a parabola. And on a parabola, the sides get closer to the middle as we go up. They don't get closer, but the slope gets steeper. I phrased that really badly. The slope gets steeper as z goes up. So it's circular when we view it from the top. That's when we have fixed values of z. That's going to produce a circle. But when we have fixed values of x or y, we view things from the side. We see parabolas. So when we build a table of, well, values and shapes, when we plug in fixed values of y, if I made this table of values where fixed values of y, put in constants for y, down here, I'm going to have a bunch of parabolas. And so we can put that together. Here's a 3/4 view of our circles. Here's the origin down here for this one. And there's our graph of z equals x squared plus y squared. Is everybody okay? No, we're all trying to draw this. Problem or questions like this is where usually the class drops into binary mode. Some of you are drawing incredibly sketchy sketches the way that I do. I'm not very good at translating what I see into what I can draw. And some of you are awesome at that. And you're going to draw these beautiful paraboloids. So if there's a homework assignment where I'm asking you to turn in a piece of paper with a graph on it, that's because some of you can draw some awesome graphs and I'm going to steal them. Reference them later on because you're like awesome artists and you know who you are. And they're like, oh, yes, I can do proper shading, unlike you, who are a terrible drawer. So we started building our library of surfaces that we can recognize. Z equals x squared plus y squared. That's going to be a circular paraboloid. What if I wanted this circular paraboloid to face the other way? What if instead of the cup going up like this, I wanted the cup to go down? What would I do? How do we change the direction of something? Multiply by -1. So if instead of z equals x squared plus y squared, if I just multiply all that by -1, that'll take all these positive numbers and flip them down below. That's taking this new thing that we talked about yesterday, and combining it with an old thing. If I multiply everything in a function by -1, that's going to flip it over whatever horizontal axis I have. And in this case, instead of a horizontal axis, I have a horizontal plane. What if I wanted to take this shape? I wanted it to move up, so I'm going to keep x squared plus y squared. I wanted to move it up or down. I want it to slide the vertex. Is it still a vertex? We'll have to look that up. I want to slide that lowest point up and down the z-axis. How do I do that? Plus c, add a constant. That's how we move things up and down. If we take a function and add a constant to it, that's going to move it up and down. See? Taking stuff that we already know and just applying it to a new object. So, modifications. If we multiply by -1, that flips a function over the x-axis, but we don't have just an axis here. If I multiply the x's and y's by -1, that's going to flip it over the xy plane. That's where our inputs are now. It's a whole plane instead of just an axis. What if I wanted to move that vertex all around the xy plane? Don't worry about up and down. I want to keep the vertex on the xy plane, keep my circular parabola grounded, but I wanted to move that around the xy plane. What do I do? What do we do? It's the same thing that happens in with regular parabolas. If we start throwing in some x terms, then we'll start moving the vertex around. And moreover, rather than just throwing in x terms, we can move things horizontally by doing addition before the function happens. Now we've moved the vertex around the xy plane. Questions? How's everybody okay? This is the correct answer because I'm kind of going deep into your memories of things that a previous instructor might have only mentioned a few times. Incidentally, when I said this is the correct answer, I was moving my hand back and forth like, oh, meh. I just realized I'm not on camera, so. Questions?
You still add that constant?
Yes.
Just moving it all around.
Yeah. If you just want to move a graph around, shifting is done by addition. So shifting the x values before this square happens is going to move things back and forth along the x-axis. Doing addition or subtraction before the square happens moves the thing back back and forth along the y-axis. Adding, here what we're doing is we have this plus c. If I subtract the c from both sides, then it's going to look like z minus c, and that's going to move things up and down the z-axis. Addition before the function happens moves things horizontally. Addition after the function happens moves things vertically. That's the old knowledge that we had that we're trying to adapt to this new environment. If you're looking for the first time it may have been pointed out to you this way, think back to trigonometry. If we think about the order of operations that happen in this function, the first thing that happens to x is subtract c. Then apply the sine function. After you've done that, add d. So this subtracting of the c is going to be a horizontal shift because it's addition and before the trig function. So this minus c is going to be a horizontal shift. And this plus d is going to be a vertical shift. Because that's what addition is going to do. It's going to shift things around. If I write x minus 3 as my input, compare that to if x is the input. If x's inputs are 0, 1, and 2, and then I replace that with x minus 3, I've taken my 0, 1, and 2 and just shifted it over to minus 3, minus 2, and minus 1. Just moved everything over. Technically, we do this in algebra when we start graphing parabolas. But all that produces is snarky comments on Facebook. And people are like, oh, I'm sure glad I remember the quadratic formula. I wish you taught me how to do my taxes. My God, dude, we taught you how to read and we taught you how to do arithmetic. Put the two together and do your taxes. You know what I mean? And we want to avoid that so much, we radicalize. Why do I have to pay taxes? You say to yourself as you're driving down a road that we all got together and paid for. Using ideas that you got from a school that we all got together and paid for. But anyway, I digress. Any questions? I'm not really that much of a statist. I just don't like bad arguments. There used to be, there was a time where we didn't have plus minus grading. And some teachers wanted to use plus minus grading. And I was like, oh, sure. I don't. I think it makes things worse. But some teachers are like, oh, no, I really want to do it. I'm like, oh, dude, all right, high five. It's like, oh, but we need official policy. I'm like, oh my God, we do. Because the computer is going to have to be told that they're going to expect plus minus grading. And I was fine with the plus minus gradings until I started seeing arguments for plus minus grading. I'm like, oh, wow, whoa, hold on. These are bad arguments. Just do plus minus grading. It's totally okay. Just do that. It's like, well, here are the reasons why. It's like, well, no. There aren't reasons why more than you just want to do it. Just do it. But we had to have these arguments, and the arguments were terrible. And so I'm like, now I've got to be the bad guy. Michael, here are why your arguments are terrible, because I couldn't let it go. I was younger and dumber back then, and I couldn't let it go. So I was taking this position that made it look like I was against people opting to use plus minus grading, and it was very uncomfortable. But that's how bad the arguments were. I'm like, oh, I'm embarrassed for you, especially when the school's like, oh, critical thinking is important. Here are our arguments for plus minus grading. I'm like, whoa, 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 those two don't match. Yo, dial it back a little bit here. Just say that you want to, and we'll kind of all be okay with it. Because a lot of people do. But anyway, I digress yet again. What are we talking about? So, on this page of notes from Calc 3, what's the only new idea that we have? It's just one new idea. That this z equals x squared plus y squared will produce a circular paraboloid. I call that new because we talked about that yesterday. And today was the first time I used the words circular paraboloid. All we're trying to do is take equation and produce a picture in your mind. This is what we did before. Take equation, produce picture in your mind. Start working out the details. Take equation, produce picture in your mind. That's all we're trying to do. That's all we've ever tried. Questions? Comments? Snide remarks? How's everybody? It's hard to tell just by looking. This is what you all look like. No matter what happens, this is what you look like. If I like pulled out that can of gas and set myself on fire, I can tell what your reaction would be. So if you do. And I just stand here engulfed in flames, trying to teach calculus. Someone will be like, "Oh, is this fire thing gonna be on the final?" All right. So this is how I want you to look at the rest of chapter 12. We're going to go through some more details in chapter 12, but remember what we're trying to do. We're trying to build a library of surfaces. Trying to take this and produce this picture in your mind. Then, once we've got those, we're going to want to learn how to modify them just by remembering how modifying functions works, what effect that has on the graph. And then we're going to want to take our calculus thinking. I've read some of your the discussions, and I like the things that you're writing in the discussion. So that's good. Keep it up. So take our calculus thinking, slope of the tangent line, area under the curve, and apply that to functions. Just taking a new thing and applying all of our old stuff to it. Any questions? I know this was a lot of me talking today, but right now, I've got to send it off to you to build the library of functions. All right, that's going to do it for today. I will see you all on tomorrow. We'll have an exercise in recognizing surfaces. Everybody have a good day, and thanks for playing. I forgot to take roll again.